In this lecture, we are going to cover the topic of pulse transfer function. The pulse transfer function plays the same role in discrete time system than the transfer function in continuous time systems. So we understand that the pulse transfer function is a very important concept in this course on discrete time system and computer control of discrete time systems. What we are going to cover today, if we look at the slide, is basically the last step in describing this interconnection. So up to this point, we saw that the interconnection of sampler and whole device can be described by a scheme of this type, where we have an impulsed sampled signal, x star of t, we have a transfer function in the Laplace domain, and then we have a certain output that in general we will sample as well, and we will get a y star of t. Now what we want to do is to complete this description in the discrete time domain. So to go on and go from this block to a z block. How do we do this? So x star of t is by definition given by this expression over here. So we have shown this relation in the last lecture. And now what we are going to show is to try to find an expression for y of t. So if we look at the diagram, y of t is equal to the inverse Laplace transform of g of s times x star of s. So we have seen that that interconnection is described by g of s times x star of s. Okay? So in other words, we have basically shown in the previous lecture that y of s is equal to this expression. Now what I want to compute is y of t. So I want to compute the inverse Laplace transform of this function over here. So to do so, this is equal to the inverse Laplace transform of g of s. And now we replace the definition of x star of s. That is the sum with k goes from 0 to infinity of xk t times e power minus k ts. Okay? Okay, now in the next step, we see that we can actually bring this inside the sum, because it does not, it's a constant with respect to k. And actually, we can bring then the Laplace transform, the inverse Laplace transform inside the sum. The reason is that for the Laplace transform, linearity holds, okay? So we can swap sums and the Laplace or inverse Laplace transform. So this is actually equal to the sum with k goes from 0 to infinity. Then this is a constant, so we can bring it outside the operator inverse Laplace. So we have xk t, okay? And then what remains is the inverse Laplace transform of g of s times e power minus k ts, okay? So this is equal to the sum with k goes from 0 to infinity of x k t times, and then we see that this is the inverse Laplace transform of g of s, and this is the shifting theorem for the Laplace transform, so this becomes a delayed version of g of t, so this is g of t minus k capital T. So this is the expression for y of t. So if we look at the slide and we extend that expression, we obtain this equation over here. So this equation is the one that we found at the board, but just written, writing all the terms of the sum. So we can write it in compact form as we have found at the board. And now we take the discrete time version of this that is given here. We recognize that this is actually a convolution sum. So if we want to compute the z transform of ykt, then this is the z transform of a convolution, and we know that this is actually equal to the product of the two z transform. So the z transform of y is equal to g of z, that is the z transform of g of t, times x of z, that is the z transform of x. So we have found now, using these properties, that y of z is equal to g of z times x of z. We can write, we are indicating g of z, with g of z, the z transform of the inverse Laplace transform of g of s, And in this course, you can actually just write the Z transform of G of S, and we understand that this means this expression. So, to conclude, we have seen that this scheme can actually be replaced by this scheme. So, if we have a plant G of S in which before the input of the plant is an impulsed sampled signal and the output of the plant is an impulsed sampled signal, then this can be replaced. We can actually compute the Z version of this, and this can be described by the simple block x of z input to g of z, and y of z is the output of this block. Before going on, I want to spend some words talking about the relation between the Z transform and the starred Laplace transform. Because we see, let's look at this block. Okay, here we can see that we have basically, actually we have shown that we have y of s equal to g of s times x star of s. Okay? And then we have said that there is a one-to-one relation up to a certain point between the starred Laplace transform and the Z transform. So one question that we may ask is that can we actually introduce an operator that is the star operator, so the star operator. And then the operation that we do when we use the star operator is that we use the star operator on this equation on the left-hand side and the right-hand side of this expression, and we get x star of s equal to g star of s times x star of s. And now, since there is a one-to-one relation between this and its Z transform, we can actually write y of z equal to g of z times x of z. So why am I introducing this star operator? Because you see that if this operator behaves well, then actually we don't have to do all the computation that we just did to show that the Z transform of this block is actually equal to this expression here. Okay? So we introduce the star operator, and we will use the star operator in the course. You have to learn how to use it. So there are some important properties that you have to understand of the star operator, and the star operator is not distributive. Okay, so this is an important known property that the star operator doesn't have. Okay, so what does it mean? It means that if, for instance, we have the star operator of h0 of s times h1 star of s, so we want to compute the starred version of this, then this works in the following way. It works that h star of s stays inside this star operation, and this can be brought outside the star operator, and then we have x star of s, h1 star of s, so this is 0, sorry. And so this is actually equal to h star 0 of s, h1 star of s, okay? Okay, but what happens if instead of having h star, h1 star, we have just h1? So if instead we have the star operator of h0 of s times h1 of s, all starred, this cannot, we cannot do anything about this. Okay, we cannot say that this is equal to h star of s, h1 star of s. So this is not true. Okay, so this expression is different from this expression. So this means that the star operator cannot be distributed to this product, and the only thing that we can do is to bring outside functions that are already starred, and then leave inside the functions that are not starred. So more in general, let's consider the example h0 times h1 times h2 times h3, where, for instance, this one is starred and this one is starred, and then we want to compute the starred version of this. Then this is actually equal to the starred version of, so the starred of h0 of s times h3 of s, all starred, okay, times h0 starred, sorry, h1 starred of s times h2 starred of s, okay? Because we can bring outside these two terms, and then what is left inside is starred, okay? So this is the algebra, basically, of the starred operator, and it's important that you learn how to use it, because we're going to use it just now, okay? And it's actually very useful in exercises to go from the S domain to the Z domain, because now if we look at this and we want to write the Z expression for this, then the Z, so if we go to the Z domain, so the Z transform of that is the Z transform of H0S multiplied H3S times the Z transform of H1 times the Z transform of H2. So you see that this is useful because we can go from here to the Z domain and we see what can be transformed and what we have first to multiply and then transform, okay? So this will be clear better in a little moment, okay? So let's go to the back to the slides. And let's now to try to find the transfer function for the pulse transfer function for more complicated situations, okay? So in this situation, this is the situation that we have just seen, okay? It's a situation in which we have the block and we have a sampler before and a sampler after. Okay, let's do this at the board. Reading from the block, y of s is equal to g of s times x star of s. Now we use the star operator, okay, and so we can write that y star of s is equal to g star of s is equal to x star of s. Now we can write the z version of this, and this is equal to y of z equal to g of z, x of z. And we have found that the transfer function y of z divided x of z is equal to g of z. So the transfer function of this block here, of this scheme here, is g of z. Now let's analyze this other block, okay? In this block we see that what is missing is a sampler between x of t and g of s. So this means that actually for the second block y of s is equal to g of s times x of s without the starred here, the star here, because there is no sampler and so there is not starred version of that signal. So if now we compute the starred version of this, we get x star of s equal to g of s, x of s, all starred, and we cannot distribute this star between the two. So when we go to the z domain, this will be equal to y of z equal to the z transform of g of s, x of s. And this is a problem. The problem is that if we want to compute the z transform, transfer function y of z divided x of z, we cannot do it because we cannot isolate x of z outside this block. So it means that in this case, as is explained here in the slide, the transfer function is not defined because we cannot write the ratio between y of z and x of z equal to basically a function, okay? We look now at the next set of schemes. So we look at the first one, and we see that here we have two blocks, g of s and h of s, and before g of s there is a sampler, between g of s and h of s there is a sampler, and after g of s there is a sampler. So now we write the transfer function here. So we have that y of s is equal to h of s times u star of s, okay? And u of s, so I'm reading from the block diagram, is equal to g of s times x star of s. Now, first of all, we compute the starred version of the second, or both of them, as you prefer, okay? It doesn't change anything. So let's compute the starred version of this, and we have that u star of s is equal to g of s star times x star of s. Because this is starred, so we can distribute the star also to this term. Now we can replace this here, and we have that y of s is equal to h of s times g star of s, h star of s. Now we compute the starred version of this, and we have that y star of s is h star of s, g star of s, x star of s. And so we can write that y of z is equal to h of z, g of z, x of z. And we can define the transfer function y of x of z as h of z times g of z. Okay? Let's look at the next example. In this example, we see that the sampler between g of s and h of s is missing. So what we will have is that y of s is equal to h of s times g of s times x star of s. Okay? Now we compute the starred version of this. And we get this expression. We cannot distribute this star to these two functions. They have to stay together. And the reason is that none of these is actually starred already. So now we can go to the z domain, and we have that y of z is equal to the z transform of h of s times g of s times x of z. And so the transfer function is well defined and is equal to the z transform of h of s times g of s. Okay? So going back to the slide, we can compare these and these. So in both cases, the transfer function is well defined. Okay? The difference is that here we have the product of g of z and h of z, because there is a sampler between g of s and h of s. Here that there is no sampler, then what happens is that g of s and h of s will have to be seen as a unique function, okay? And we have to compute the z transform of the product of the two functions. Let's now look at this other example at the bottom. Here we have that y of s is equal to h of s times u star of s, because we have a sampler between, we have a sampler here, so we have u star, okay? And then u of s is equal to g of s times x of s. And the reason why there is no star there is that in the slide you can see that there is no sampler over here. Now if we compute the starred version of this, because we have to replace it here, we get u star of s equal to g of s times x of s all starred. Now we replace this over here, and we get y of s equal to h of s times g of s x of s all starred. Now we star everything, and we get y star of s equal to h star of s, and this is g of s times x of s all starred. We write this z transform, and we get y of z is equal to h of z times z transform of g of s at x of s. So we get this expression, and the problem is that for this expression we cannot define the transfer function, because y of z divided x of z is not well defined, because we cannot actually isolate x of z. So here we see that for this case the transfer function is not defined. Before going on to the next example, I want to introduce a notation. When we have the function z of g of s times x of s, so we have to compute the transform of the product of two functions in the Laplace domain. We can indicate this as the z transform of gx, so we remove the argument and we put them together. We use a label, basically, this is a label. And again, we can indicate this as just gx of z. So gx of z is indicating this z transform. Let's look at this more complicated example. So here, the computation is done on the slide. So we want to write the transfer function between y and r, okay? So we start to write the relation between y of s, okay, and e star of s. So y of s is equal to g of s times e star of s. Then we want to write the relation between e of s and y of s. So e of s, okay, is equal to r of s minus h times y of s. So we get these two expressions. Now what we do is that we replace in y this y here, and we get this expression here. Now we compute the starred version of these two expressions, and we get this expression over here. Note that here there is the starred operator over h of s times g of s, okay? Now what we do is that we solve the first equation with respect to e star, and then we replace it in y star, and actually we get this expression over here. Now the last step is to replace the star Laplace transforms with the z transforms, and we divide also for this term, and so we get that the transfer function between yz and rz is defined in the following way, where gh of z means the z transform of g of s times h of s, okay? Okay, so this is actually, I want to point out that some things here are expected. In particular, it's expected that somewhere it will appear the term gh of z. Because if you look at this diagram, you can notice that there is no sampler between h and g. So between h and g, there is no sampler, because the sampler is put after the feedback branch. So this means that at one point we will have a z transform of h of s times g of s, so the z transform of the product, because there is no sampler. So this actually happens in the feedback branch, and actually we will have this at the denominator. So if you remember how to work on block diagram since previous courses on control, you can see that, you understand why this happened at the denominator. And instead, at the numerator, we have just the branch g of s, so the function g of s, and so we get this expression here. So we have seen a lot of examples. Now let's try to put everything together and give a procedure to solve these exercises. So the first step in the procedure to solve block diagrams is to introduce variables names if the variables names are absent. So if you get a diagram here without any label, so there is no r, no e, no y, first thing that we do is that we introduce some labels. So we call the output y, we call the reference r, and we call the error between this reference and this feedback branch e, okay? These are labels, you can call them as you want, okay? Then once that you introduce the labels, you want to express the output of the blocks, okay, in function of the input of the blocks. So here, what we do is we write the output of the block gs as a function of the input of the block gs, and we get this expression here. And here, we write the output of the block. In this case, actually, we write the variable just before the sampler, e of t, e of s, as a function of r of s and what is before the block, so y of s, and we get this expression here. Then the next step is to transform this equation in the starred version, so we obtain this expression over here. Then we solve the equation to find the relation between the output and the input, like in this case. And finally, we can express the result in terms of the z transform. And so we obtain this. So this concludes this lecture on pulse transfer function. In this lecture, we have introduced the concept of pulse transfer function, and we have also introduced the star operator and how the star operator works, and how to solve block diagrams to find pulse transfer functions or complicated interconnection of systems.